So now we've been talking about shock waves, expansion fans, etc. for some time now, right? Now going back to Laval's experiment, where he basically passed steam through a certain type of a duct, converging diverging nozzle, and he was able to get supersonic flow. Now we haven't done anything to that respect, right? We haven't really said that how, if I what exactly is the relationship as to how much there should be an area change so that we can get a certain change in Mach number. So we'll do that now and see some things interesting. Okay, now let us consider this interesting thing in the sense we've talked about this before, which is a quasi 1D flow. Okay, now if you have a duct like this, right? So here this has an area A, and this is a constant area, right? So this is a 1D. You can say this is 1D. But what if you have something like this, or if you have something like that, right? So in this case, as we had said, right? So if you have a reference frame, say like this. So therefore, basically at every x location, you have a different area, okay? But that area doesn't change in any other direction at that particular location. Therefore, this is called a quasi 1D flow, okay? So let us see what we can do with something like this. Okay, so say we have a quasi 1D flow, right? So we here A is basically Ax, and you have pressure, temperature, density, velocity, etc., etc. Right? Now let us do a thing. Let us take a particular location here, and let us take another particular location over here. Right? So then in that case we have P1, T1, rho 1, U1, A1, so on and so forth. Right? Now we know from the equation of continuity that right? Now this is from the equation of continuity, right? So therefore what this means is that right, which means that rho A into U is constant, or it also means that right, that is simple. Okay, now if I have this, okay, now let us differentiate, okay, without going into the details of the let's just say high school math. I'll just go ahead and do this. Okay, so I'm going to differentiate this. Okay, if I differentiate the above equation, what I get is right. So we get if I differentiate, I get this, and let's call this as equation 1. Okay, so we have a certain relationship between density, area, and the velocity. So a relationship between the changes in density, area, and velocity. So if you change the area, there is a corresponding change in density and velocity. Okay. Now similarly, from the momentum conservation equation, we get this. So, from the momentum conservation equation we get this. Okay. So, in this case, and let us call this as, say, the second expression. Now, from here let us write it like this. Right, this is equal to, yeah, okay, or this this term is something that we will write like this. Okay, this term, say, now this term is something that we will write like this. Now dp, so now you will know where we are getting at. Okay, you see, I just choose to write it like this. Okay, so we get this from the momentum equation, so I just rewrite it in this form, and then this is something I write like this. Okay, now d rho by rho is something that we get in this particular expression over here. Okay, now if you remember, dp t rho right, where a is the speed of sound. Now, this is something that we've sort of done before. So, for the velocity of sound is related to dp by d rho, the change in density with the corresponding change in pressure, right. We've done this before. So, what we can do is replace this term dp by d rho by this a square, right. So, what we get is, right, into a square is equal to minus u into du, or we can write this as d rho by rho is equal to minus u by a square into du. Again, this we can write as minus u square by a square into du by u. So, this you can see we can write as m square du by u. Okay, so what we can do now is, coming back to equation 1 here, we can write this d rho by rho, right, in terms of Mach number. So, what we can do now, let us do this over here. Okay, so let us sort of rewrite this. So, this is the equation we have. So, we have this d rho by rho plus dA by A plus du by u is equal to this, right, and we found out an expression for this. Now, this is something that we can write as minus m square du by u, right. If we write that, then what do we get? What we get is 1 minus m square du by du plus dA by A is equal to 0, or we can write this as dA by A is equal to m square minus 1 by u. Okay, now so what we have done here is basically using the same old governing equations, right. We use the continuity equation and the momentum equation, and we connected the speed of sound, right, to those equations, and what we are able to get, that for a given Mach number, if there is a small change in the area, there is a corresponding change in the velocity. Right. Now, let us hold this equation dear, and we are going to come back to this and see what this physically means. Okay. So, let us call this is basically the area velocity relationship. So, let us call this, say, equation as 3. So, let us keep this, and we are going to revisit this in a bit. Okay. All right. Now, again, let us go back to our continuity equation and do this stuff. Okay, so now let us say that okay, let's say Okay, so say this is a location, okay, this is a location and this is another. So say this is location 1 and this is location 2. So this is area, pressure, temperature, density, velocity, okay, and this is area. So say A1, P1, T1, rho 1, U1, A2, P2, T2, rho 2, U2, okay. Now let us consider this location 1 as a throat, if you remember what that is. So this is a location where the Mach number is equal to 1, okay, and we denote this the throat by a subscript star, if you remember, right. So what this becomes here is a star, okay, this becomes say P star, this becomes T star, this becomes rho star, and this is equal to U star, which is equal to A star. So that again M1, right, is equal to M star, which is equal to 1. So this is essentially my throat. So this is my throat, okay, and in here we're going to just call that as say A, P, T, rho, U, and we say will have M2, so that is equal to M. So basically we are looking at a particular location, and we are going to look at that location with respect to the throat, okay. Now let us see if we get any special information by studying this, okay, right. So again, so we have this, we're going to play around with our equations and the variables. So again what we have is rho 1 A1 U1 is rho 2 A2 U2, right. We have this. Now what we're going to say is that 1 is the throat, isn't it? So if 1 is the throat, then we write this as rho star A star U star, right. This is equal to rho A and U, isn't it? Now this U star again, this of course becomes, okay, so then what I write this again, or we can write this as rho star A star, that's the area, this is the speed of sound, is equal to rho A and U. This is what we get, right. So therefore we can write rho star by rho, right. This is equal to A by A star and U by so that is equal to A by A star, okay. So or let us write this say A by A star, okay, A by A star is rho star by rho into A star by U, right. We have this in here, okay. Now again, so basically this is something that we get by applying the continuity equation between the throat and any other location, okay. Now if you remember, we have relationships like this. We have talked about these relationships before, right. Right. So this is the stagnation density. So we have similar relationships. So stagnation density, the ratio of stagnation density and density at any location is a function of the Mach number, right, and this gamma is given for a given gamma. Now this is something that we've developed before, isn't it? So and this Mach number corresponds to this density, in the sense that at a particular location the local density is rho and the local Mach number is m. So, then the relationship of that local density and Mach number with the corresponding stagnation density is this. Okay. So, this now therefore, if I say the local density corresponds to the density at the throat, so then this becomes star, isn't it? So, this becomes star, and I can sort of write this. So, if I may write that, and this becomes m star in that case, and we know that m star is equal to 1, right? M star is equal to 1. So, therefore, so this basically becomes 1. So, what we are left out with over here is this, right. So, what we get is gamma plus 1 by 2 raised to 1 by gamma minus 1. So, rho star by rho naught by rho star is basically just a finite number, okay, for a given gamma. Okay. So, therefore, you know, so yeah, this is it. And then, okay, then again here, okay, now here you can clearly see that A star by u is equal to 1 by m star, isn't it? This is 1 by m star, and we also have this m star. Okay. Now, m star we have seen from before that m star square is also related to the local Mach number as so. Right, the local Mach number is related to m star as so. Okay. Now, what we are going to do is, so therefore, what we are going to do is, okay, so essentially write this in this form. So, we have an expression for this in terms of the Mach number, and how are we going to do this? We are just going to play around with that, and we are going to say that this is, so this is equal to A star by u, right. So, what we are going to do here is we will say right, we get this. So, now for rho naught by rho we have an expression in terms of m, and rho star by rho naught we have an expression which is equal to this. So, therefore, we have an expression in terms of yes. So, rho naught by rho star is this, right. So, this is a term which is equal to this, and rho naught by rho is equal to this term which we used originally. So, this is basically a function of the local Mach number, and this also is a function of the, so this is also a function of the local Mach number, right. So, if I write that out, okay, if I write out the equations in that fashion, what I will get is this. Okay, let me come back here and write it. So, then what I get is A by A star, right, this is equal to 1 by m square, okay, 2 by gamma plus 1, so 1 plus gamma minus 1 by 2 m square, okay, to the power gamma plus 1 gamma minus 1. Okay. So, now let us say this is okay. So, essentially what we did over here, now this is a very important relationship, or a very interesting relationship, is that you can also see from here is that the local Mach number here, see, the local Mach number, the Mach number here is a function, right, of the ratio, is a function of the ratio of the local area to the area at the throat. Okay. So, this Mach number here, this is a local Mach number, this is a function of the ratio of the local area and the ratio of the local area and the throat area. Okay, and what you can see over here is that for for say a given Mach number, you can get for a say throat, at the throat the Mach number is 1, right. So if I go along say a duct, like I go along a certain path and I need say a certain Mach number, say I need say 2.5 Mach. So given that Mach number, you can relate the change in, you can get the area required. So you need to find out the total area change that will be required to go from say Mach is equal to 1 to Mach is equal to 2.5. So that is what is given in this relationship. Now mathematically speaking, what this is doing is basically for a series of Mach numbers you will get a series of ratios like this, right. So for say a given area at the throat, you can get several, you can get relations for this area, okay. And you can see here that for a given area basically you have 2 values of Mach numbers over here. Now what I have done basically in here is that I have just plotted this, okay. I have taken a series of, okay, let me just say what exactly I have done and I will show you that and everything, okay. So I said that I am going to go say this is my x direction and this is my y, right. So I will go along say this direction, say from 1 to 2 to 3 to 4 to 5 and so on and so forth. I will go along x, and at each section I have a different Mach number, right. Now this is a Mach number of which I am going to give. So say this is Mach 0.02 and then it goes up like that. So say here Mach is equal to 2.5. So as I move along say this distance, right, I am also I'm going to change the Mach number of my flow, and this is something that I am doing. And corresponding to this change in Mach number, I am calculating the area change, right, area change. And let us just say for conjecture's sake that A star is equal to unity. So then I can get, so say area at the throat, this is just for a test case. So we will then be able to calculate the area at each location. So area here and area here, okay. So what I am going to do here is, what I have done is do 2 cases. One is Mach is supersonic and the other case the flow is subsonic. So we will do these things. So what I have done again is gone back to Scilab and plotted this, and let us see what we get, okay. Now we said that we will come back and talk about this as to what this physically means, right. So in this you can see that I am going to, like I said here, I will make Mach subsonic, and supersonic. So if I do that, this has a certain mathematical implication, okay. So we will come back and look at this. Now before that, let us go and look at the Scilab code here, okay. Now what you see in this, basically this is the code that I have, right. So what I am doing here is that for a gamma, as you can see, it is a gamma 1.4, right. So then if I come here, so what I am going to do is go from do this for a supersonic flow, right. So I am going to go from say a starting Mach of 1.02 and go up to 5, okay, and the Mach number increases by 0.02, okay. And the locations, this is something that I have come up with, okay. So locations I basically go from say 0, okay, and I increment by 0.25. So at every 0.25 location I have a different Mach number, and what I am going to do is calculate the corresponding area change, right. So I enter the Mach number here and then I calculate the area change. So, A location by A throat. So, we get that, and hence we will, so we will go ahead and do this. Okay. So, having done that, what I am going to do is run this. Okay. Okay. So, what you can see over here, that as I go, this is my x direction, you can see this is my x and the corresponding change in Mach. So, the Mach is I am basically changing linearly in this case, right. So, what you can see, this has gone up to 5. So, if I may sort of increase over here. Okay, why am I not able to do that? Okay, so I think if I do this, then I should be able to do this, right? Okay, for some reason I am not able to do that. Okay, so basically we are going from 1.02 here, right? I have not done any sonic conditions, that is what I wanted to show actually. Okay, so if I do that, so then this is the increase in the Mach number. Now, let us look at this. Okay. Now, what you see over here is that this is the change in the Mach number as we go from 0 to 50. This is along the distance. So, along x, as you go in this case, right, what you have here is that as you increase the Mach number, the area has also increased, right. As you increase the Mach number, the area has also increased, but this Mach number is the entire flow here is, however, supersonic, right. For supersonic flow, therefore, as I increase the area, as I increase the Mach number, the area is also increasing, which means that the flow speed is increasing. So, this is supersonic here, right. So, for a increase in area, there is increase in the velocity. Okay. Let us go back to this equation over here. Just look at this. If Mach number is positive, right, if this is supersonic, therefore this is positive, which means for a positive change in the area, there is a corresponding positive change in the velocity. So, which means that for a supersonic flow, right, with area increasing, the velocity also increases. Okay. Now, let us then go back. Okay, let us rerun this. Okay, let us rerun this. So, let us go say back over here, or say let us go here. So, let us go back to the code and let us say that we are going to run this only for subsonic cases. Okay, we are going to run this for subsonic cases. So, say this is running from just below this and it goes to 2, right, and that decreases. Okay. So, this is what we get over here. So, we are going to go from the flow is subsonic in the entire region. Okay. So, if I do that, okay, now if I do that, so let us do this. Okay. We are going to run this again. Okay, that is Scilab for you essentially, right. So, if I do this, so again as you can see that over this range, basically over this range, okay, we have the Mach number which is decreasing, right. Now, you can see previously where we went from 0 to 50, okay, when we went from say 1.02 to 5. In this case, we are going from 0.98 to 0.02. Okay. So, this is 0.98 to 0.02. This is my change in Mach number. Let us look at the corresponding change in the change in the area. So, what you see over here is that the flow is subsonic. The flow is subsonic in the entire region. Now, as you increase the area, however, the area increase, as you can see, is quite gradual, right. This area increase is quite gradual, and there is area also increases, right. So, in this case, so therefore, the velocity is decreasing, isn't it, because in here, as you see, the Mach number is decreasing. The Mach number decreases in a subsonic flow. So, if the Mach number is decreasing, then in the area is increasing, but Mach number is decreasing, which means the flow is slowing down. So, therefore, in a subsonic flow, if the flow is totally subsonic, right, there is, say, an increase in the area, right, but the velocity decreases, right, as you can see. So, therefore, this is essentially the difference between supersonic and subsonic. Now, let us come back to the equation. Now, if this is subsonic, right, that will make this as negative. So, which means that if that for a positive change in area, which is a plus dA, this becomes a negative du, which means that there is a slowing down of the flow. In other words, if this is negative, then say this becomes negative. So, which means that if I increase the flow velocity du, then there is negative A, which means the area has to decrease. So, therefore, if the flow is subsonic, and you need to increase the flow velocity, then you need to decrease the area, right. Whereas, in a supersonic case, if you need to increase the velocity, you need to increase the area as well. Okay. That is what we see from the equation here, and as I plotted, this in this Scilab. So, you can see for yourself how these two sort of give us a lot of information. Now, what we will do is we will make this thing run for a series of we will let it go from, say, subsonic to supersonic. We will let this run from 0, right, we will let this run from 0 to 5, and this will go to 0.02, right. So, this is what we will make this do. It goes from a subsonic Mach number of 0.02 and it goes to Mach number of 5 in steps of 0.2. Okay. If we do that, let me go ahead and run that. Okay. So, if I do that, okay. Now, if I do that, so what I get is this. So, what you can see now that when I do this, it goes from 0.02 to 5. So, this is my throat condition, which is being reached around, say, the distance 10. So, what I see over here is this, right. So, what you see over here is that beyond this 10, so beyond this distance, flow is supersonic. So, for supersonic, as you increase the area, the Mach number is increasing, right. But in the which means the flow is traveling faster. In here, however, we are going from there is a decrease in the area as we increase the Mach number, and this is the subsonic zone. Okay. Now, let us talk about this region. So, we divided this region, we said this part, so this part, say, beyond 10, this part here is the supersonic zone, and this part is the subsonic zone. So, what do we have over here, right? So, we went from 0.98 and then we went to 1.02. So, what happens in this region? Now, this here is basically, as you can see from this diagram also, it is basically the least area, least area in the entire distribution, right. So, this is where it goes through a Mach 1. It goes through a Mach 1. So, if you come here, and you do this for a Mach 1, you will get a corresponding. Now, that is essentially the throat region, and I have just taken that, in this case to be basically the least area. So, based on that, we will get the areas of the rest of the duct, so to speak. So, now if you look at this, if you put m is equal to 1 here, it kind of does not make too much sense, this relationship does not hold. So, what essentially this equation here would mean, that physically what that means, that it is the least area in the distribution, right, that is the least area in the distribution. And so, the flow when it is going from, say the flow when it is going from converging to diverging, passes through this point, right. It passes through this point, and what we get is a supersonic flow. So, what essentially you are having here is that a subsonic flow, it goes through this kind of an area change and becomes supersonic. So, this is what something that Laval had done long time back, right. So, this is essentially your converging diverging nozzle. Okay. Now, based on that, let us do a quick problem, and we will see how we are going to use this. Okay. Before I move forward, what you can see here is that for a given Mach number, this can be given, which is exactly so, because this is also available in the tables. So, like I was getting over here, so let me just show you. Yes, so this is so what you will get in the tables is from point, say 0, 2 to 5, you will get the corresponding areas. Okay, you will get the corresponding area changes like this. Okay, so that's what we get. Okay, so now let's do a quick problem and sort of wind up our understanding of this. Okay. Okay, so what we have is, so we have an isentropic flow through a convergent divergent nozzle with an exit to throat ratio of 2. So, we have an exit to throat ratio of 2. We have this area, right. Now, whether you want to do this over a length of 50 or 1 is really up to you, but when we will come to a place where we will also talk about minimum length nozzle, and that is a theory that we will talk about later on. Okay. Okay, the reservoir pressure and temperature are 1 atmospheres and 288 Kelvin respectively. So, basically the chamber in which you are developing, you are producing the fluid, right, the gas. So, the reservoir temperature, so I am going to call that as is 1 atmospheres, this is given, and T naught is 288 Kelvin. So, what we need to find out is calculate the Mach number, right. So, the pressure, temperature at both the throat and the exit. So, we need to find this out at the throat and exit, okay, for 2 conditions. Number 1 is the flow is supersonic at the exit. The flow is supersonic at the exit, and number 2 is the flow is subsonic throughout the nozzle except at the throat where it is 1, right. The flow is subsonic everywhere, right, everywhere except of course at the throat, right, where it is equal to 1. Okay. So, how do we go about and do this? Okay. So, what we will do is this. Okay, we will use this, we will need to find out now we do not know any throat conditions. This is all that is given to us. The stagnation conditions are given and the area ratio is given. Okay. So, all we will do is find these out, P star by this, right. How we will find out? So, basically in this case what we are going to get is that this is basic. So, what is given in the tables is this. What you will get in the tables is this. So, this is the local Mach number. So, what we will do is find this out for at the throat. So, which means my local Mach number is 1. So, corresponding to that we get P star by P naught is 0.528 and T I get as I get this, right. So, therefore, order to calculate the so say we need to calculate the right. So, P naught is given and T naught is given. So, therefore, we get the throat conditions. So, we get P star as 0.528, right. We get a throat conditions and T star is equal to 288 into this. So, which we get at 240 Kelvin. So, these are my throat conditions. Okay. So, one easy step we get this. So, now next is that we basically have to find out okay. So, now supersonic flow. Okay. Now, for the supersonic flow, if it is supersonic, right. Now, if you look at the tables, what you will get is there is a Mach number and there is a corresponding area ratio. So, local area by the throat area. So, this is what you will get. What we are given here is not this, what we are giving here is this, right. We are not given an incoming Mach number. We just know the area ratio. We knew the stagnation conditions from which we can calculated the throat conditions, right. And in here what we are given is this. So, corresponding to this being 2, we calculate the corresponding Mach number and what we get that is 2, right. So, what we need to calculate is Mach number, pressure and temperature, right, at the throat and exit. So, throat is something that we have calculated. What we need to calculate is at the exit. So, now corresponding to the exit area ratio, which is of 2 with the throat, we get a Mach number of 2.2. So, the Mach number at the exit is 2.2. So, this is equal to my Mach number at the exit. So, what we need to now calculate is pressure at the exit and temperature at the exit. What we know are the stagnation conditions. So, what we will have to calculate is Pe by P naught into P naught, right. Now, Pe by P naught is something that we will get again from the isentropic tables, right, corresponding to this Mach number. Corresponding to this Mach number. So, corresponding to this Mach number, we will get that, and what this comes out to be, right. So, what we get over here, so this and P naught is equal to 1. So, what we get over here is 0.0935 atmosphere. So, similarly for this here temperature, so Te by T naught into T naught, right. So, again this is something that we will get, this is something we will get in corresponding to this Mach number, and this comes out to be 146 Kelvin. Okay. So, therefore, now since we know, now if you go to the tables you will see that it runs from 0.02 to 5. So, which means it goes from subsonic to supersonic. So, when we calculate this Mach number, we have to look at the supersonic part of the table, right, because there will be 2 values. So, for this area ratio, we go to the supersonic part of the tables, and that is where we get corresponding Mach number, which is 2.2, and corresponding to that from the isentropic tables we can find out this. Now, for the second case, which is subsonic, right. So, what we do now is go to the subsonic part of the table and calculate the corresponding Mach number. So, and the Mach number in that case comes out to be, exit comes out to be 0.3, right. And again we do the same procedure corresponding to that Mach number, we will now calculate the pressure and temperature, right, using the same same way. And what I get here is this. That and the corresponding temperature is 282.9. Okay, so that's it. Okay, so what essentially we've done here is that from just this information, all we have, see, all we have here is that we know the pressure and temperature of the chamber in which the gas is being developed, and all we know is the physical dimensions, the area of the exit by area of the throat, that's all we know. But we've been able to calculate a host of information from using the very simple tables by using our knowledge. Okay, so and so basically what we we were able to basically use these relationships, right, develop the tables and use it for something something simple but interesting. Okay, all right, that should be all. Thank you.